I'm excited to welcome you to this course on building interactive agents with generative UI, built in partnership with CopilotKit. Building a capable AI agent is hard work, but once you've done that, you get a new challenge, getting it to users in a way that they enjoy interacting with it, which might require much more than building yet another chatbot interface. Think about what a good agent interface might look like. Instead of it outputting long paragraphs of text, maybe the user would rather just get a simple form to fill or a chart to interact with. The agent doesn't just answer in plain text, it can give the user something to see or act on. In this course, you learn to build that interface using 3 approaches to generative UI, where the UI, the user interface, is generative. The first approach is controlled components, where you define exactly what the agent can show. The second is declarative UI with the framework A2UI, which is an open spec originated by Google and co-developed with CopilotKit, where the agent generates layouts from a schema. The third is open-ended UI with MCP apps, where the agent surfaces full interactive experiences like whiteboards and approval flows directly inside your product. Your instructor is Atai Bakai, who is co-founder of CopilotKit, the team behind the AGUI protocol that this course is built on.
Thank you, Andrew. Every interaction between people and technology is increasingly mediated by agents. And yet, as we film this course, most agents still talk to users in plain text, which is a lot like the command line MS-DOS era of personal computing. Powerful for early adopters, but not yet built for mass adoption. The Windows and Mac era changed that and brought full-featured applications that anybody could use. AI is going through the same transition now, and all UI is becoming AI. When a user asks for a report, the agent should build it. When they need to approve something, the agent should show them a form. When they need to explore data, the agent should render a chart. You'll start by connecting a LangChain deep agent to a React frontend using CopilotKit and AGUI. From there, you'll build across the full generative UI spectrum, from controlled generative UI with handcrafted components that render on demand, to declarative generative UI, where the agent assembles UIs from a component catalog of building blocks, to open-ended generative UI, with app experiences powered first by MCP apps and then by full app sandboxes.
By the end of this course, you have built a full-stack agent app that renders charts and cards on demand, surfaces a live whiteboard through MCP apps, and keeps a shared to-do list in sync between the agent and the UI. CopilotKit is open source, and it supports all 3 of the major generative UI patterns in one framework. It also has first-party integrations with LangGraph, Google Cloud, AWS, Microsoft Azure, and others. Many people have worked to create this course. I'd like to thank from CopilotKit, Uli Bakai, and Tyler Slayton. From DeepLearn.ai, Summer Ray also worked on this course.
In Lesson 1, you'll walk through the 3 major pillars of the generative UI spectrum side by side, what makes each one different, and when you'd use each one. By the end, you'll have the mental model for everything you're going to build in this course.
So let's jump in and get interactive.
About its 3 key pillars: controlled, declarative. I'm Atai. I'm co-founder and CEO of CopilotKit. In this course, you will learn to use the open source CopilotKit stack in the AGUI protocol, which has been adopted by Google, Microsoft, Amazon, LangChain, Oracle, and many of the other leading agentic ecosystems. So everything you learn here can apply across the entire popular agentic stack. In this lesson, you will learn about the generative UI spectrum and about its 3 key pillars: controlled, declarative, all the way to fully open-ended generative UI, and about what makes each one of those parts different and when to apply each. By the end of this lesson, you'll have the mental model for everything you're going to be building in this course. So let's go. All right, let's jump in. I want to start the course with a bit of a provocative statement. Over the next few years, all UI will become AI, meaning every interaction between humans and technology will be increasingly mediated by agentic systems. Of course, this is true of complex software products like HubSpot, Zendesk, Figma, and so on, but it may even be true of your refrigerator. That might sound a little bit preposterous, but wouldn't it be nice if you could walk by your refrigerator and tell it to order the missing ingredients for tonight's lasagna? So that's where we're going: ubiquitous interactions between agents and humans. But where are we now? Current agentic interfaces look a lot like the MS-DOS command line interfaces of the 1980s. These initial raw interfaces are good enough for early adopter types who drive the lion's share of initial use, but they're not good enough for mainstream mass adoption. To continue this analogy, today's agents are beginning to graduate from the MS-DOS era to the Windows and Mac era. If you're paying attention, you've likely noticed your customers are asking for this loudly. In this course, we will walk you through the concepts behind building full-stack agentic applications which are ready for mass adoption. Great full-stack agentic applications leverage generative UI capabilities to build a great user experience for working alongside agents. For example, in Claude Code and in Cursor, we're able to seamlessly work alongside our agent and see what it is doing and steer it in coherent steps. In Notion, our agents are able to take actions on our behalf in the application right as we work. In Manus, our agents stream to us what they're doing and present with a nice UI. So why is building all of this so hard? Developers who first approach agentic application development start by focusing on the agent itself. They initially expect that once they build the agent, they'll just throw it behind an API and connect it to any user-facing application, just like they've done with every front-end and back-end development before agents came along. But when we try to do that, we run into a second and initially unexpected set of problems. We discover that agents break the request-response paradigm, which has been powering the internet for the last 30 years. Agents are, of course, just software, but from the standpoint of pre-agentic software, they're a little bit like a weird bird. They're long-running, so they have to stream their work as they run and support reconnections, interruptions, and mid-run steerings. They have to support structured and unstructured data exchange at the same time. You have text and voice alongside tool calls and state update and so on. So it's a little bit like implementing Slack and Zoom in a traditional application all at once. And there's really a long list of these peculiarities that agents have from the standpoint of pre-agentic software. And so when we try to stick an agent behind a traditional API, we end up running into wall after wall after wall of complexity. And we discover that we have to re-implement 30 years of glue code, which we've all been taking for granted for the agentic age. And that's where CopilotKit and AGUI come in. CopilotKit provides open source developer SDKs and a cloud platform for building user-facing agentic applications in a way that's optimized for the agentic era, as opposed to retrofitted from the request-response paradigm. The AGUI protocol, which stands for the Agent User Interaction Protocol, lets developers who build agent frameworks and harnesses bring their agents to user-facing ecosystems by building against a robust standard, which means they conform to a few simple requirements and everything just works. This in turn allows developers and organizations who build agentic applications to build against all of these different agents in a streamlined fashion. To situate AGUI in the landscape, you have obviously MCP, connecting agents to third-party tools into context. You have A2A, connecting agents to other agentic systems. And AGUI is the third leg of this triangle, connects your agent to user-facing applications. AGUI emerged from our initial partnership with LangChain and Kurai, and since we launched the protocol, it's been widely adopted by many of the top leaders in the agentic space, which means that everything you learn in this course can be applied to any agentic system you work with out there in production. By the way, if you do come across a system that is not yet supported, or if your organization made its own agentic system, you can also build your own AGUI connectors for that system. However, we will not cover that side of the equation in this course. So you can use AGUI to connect any agent to your users, but you can also use AGUI to connect any user to your agents. Everything you will learn in this course can be applied to building agentic applications in any front-end your users use, from web to mobile to Slack to text messaging and so on. In this course, we're going to focus on web, and specifically on React, which is the dominant web framework. So having laid out the architecture, let's bring our attention back to the world of generative UI. First, what is generative UI? Generative UI is a UI paradigm which is both enabled by and exists in service of LLM systems and agents. What does that mean? Well, LLM systems and agents introduce both new capabilities and new challenges to the software landscape. Generative UI is the UI paradigm that takes advantage of those new capabilities, both to improve experiences and to address those new challenges. Generative UI solutions exist on a spectrum where control flows from the developer to the agent. There are three pillars in this spectrum: controlled generative UI, declarative generative UI, and open-ended generative UI. The entire generative UI spectrum is needed in modern agentic applications because different solutions along the spectrum have different pros and cons, and so are best suited for different use cases. In this lesson, we will briefly outline the three pillars of the generative UI spectrum, and then in the rest of this course, you will dive deep into each one and learn how and when to apply it. Controlled generative UI is a paradigm where the developer provides the agent with pre-built, fully custom UI components that the agent can call upon as needed to augment an interaction. It allows for maximum customization and predictability and pixel-perfect designs. Controlled generative UI also allows for a straightforward development experience familiar from the pre-agentic backend front-end era. Controlled generative UI is considered the workhorse of the generative UI world because maximum customization and predictability are important for your product's most used surfaces. The downside of controlled generative UI is that you have to design a specific component for each interaction you want your agent to support, and so implementation complexity scales linearly with capabilities. We will implement controlled generative UI using AGUI and CopilotKit in this course. Declarative generative UI is a paradigm where developers declare a component catalog of pre-built Lego-like building blocks, which the agent can then assemble into rendered components dynamically and on demand for any given interaction. Under the hood, the agent returns a structured schema that represents an assembly of building blocks, along with data bindings containing values that fill in that schema. The schema and the data bindings are then passed to front-end renderers, which can visualize the structured content as native UI components. We will soon see an example of this in action. In consumer-facing applications, declarative generative UI is most suited for the long tail of product surfaces, where flexibility is more impactful than perfection. Declarative generative UI also excels in internal applications that generally favor pure functionality and ease of implementation over a perfectly optimized user experience. The reason is that declarative generative UI cannot be made pixel perfect. Components have to consist of a standard combination of pre-built building blocks. Declarative generative UI is also less deterministic than controlled generative UI. The same user query may be answered via a different combination of building blocks at different times. And because it requires more computation and generation time, it is also slower than controlled generative UI. The tools we will use here are CopilotKit and the A2UI spec, which is spearheaded by Google. CopilotKit and AGUI are launch and design partners on A2UI, and AGUI allows you to use the A2UI spec with any agentic backend. Further along the generative UI spectrum, we find MCP apps, which are an official extension of MCP. MCP apps are widgets and even fully featured applications that get embedded inside the AI chat window. Under the hood, MCP apps are implemented via an embedded iframe. MCP apps are supported by the ChatGPT and Claude app stores, and they are deeply optimized for those app store use cases. The advantage is that you can bring any third-party app into a chat experience while allowing it to keep its branding and without having to customize the host app in any way. The disadvantage is that this constraint necessitates an inherent indirection in the interaction between an MCP app and the host, which introduces additional implementation complexity because you're implementing essentially an app inside of another app, security challenges, and limited customization outside of the MCP app window. Additionally, today MCP apps are inherently tied to an iframe implementation, which means they're less suitable for experiences that exist outside of web, such as mobile or Slack. In this course, we will take advantage of the handshake between AGUI and MCP apps to bring any MCP app, including those apps originally built primarily for the ChatGPT and Claude app stores, into your own custom agentic applications, which means that your users can bring the apps they're already familiar with, from Salesforce and HubSpot to Figma and Spotify, into your own custom agentic application. Finally, at the very far end of the generative UI spectrum, we find fully open-ended generative UI. This paradigm consists of UI that is fully generated by the agent on demand per user request. Fully open-ended generative UI is often what people have in mind when they first hear the term generative UI. This paradigm of generative UI is most suitable for the far long tail of user queries and for delighting users with custom and boundless experiences that by today's standards are unexpected. That said, fully open-ended generative UI requires far more thinking tokens to work, which is both slower and more expensive, and it is far less predictable and robust than alternatives in the generative UI spectrum. It's currently still in the experimental phase of adoption, but it represents the full promise of agentic UI and captures our imagination. Given the tremendous pace of development in the agentic space, it will likely quickly become more and more production ready. In this course, we will implement fully open generative UI using CopilotKit and AGUI middleware, which means you can bring it to any agentic backend right away. Let's do a quick recap. As you will soon see up close, the different parts of the generative UI spectrum have different strengths which are suitable for different needs and surfaces. Controlled generative UI, the so-called workhorse of the generative UI world, is the most appropriate solution for the most used surfaces in your application. Declarative generative UI, which is more flexible but less customizable and deterministic, is most suitable for the long tail of surfaces in your application. And open-ended generative UI is most suitable for interacting with third-party systems and for the late long tail of your application. I'm really looking forward to going on this journey with you. We will begin the course by building a basic agent chat UI on top of a solid foundation we can continue to build on. Then we'll go over controlled, declarative, and open generative UIs with hands-on examples for each. Finally, we will close out with additional building blocks needed to create a great full-stack agentic application outside of the chat, including front-end tool calling and state synchronization. This is a quickly evolving and emerging space, and I really hope this course will get you ahead of the curve. In this lesson, you'll build your first agent chat UI on a production-grade foundation that you can customize and continue to expand on. You'll use CopilotKit and AGUI to connect your React frontend to a LangChain Deep agent, as well as to a Google ADK agent. Throughout the rest of this course, we will expand on the foundation here with a full generative UI spectrum. All right, let's get coding. Throughout this course, we're going to augment our agent beyond the text-only chat experience. But before we do that, I want to take a minute to talk about the lasting value of chat. LLMs first broke through the public imagination with the launch of ChatGPT in 2022. And ChatGPT was, of course, first and foremost, a chat experience. Many people predicted that chat would be a quickly passing fad and that it would be replaced by a more traditional interaction modality. But LLMs have come a very long way since the original ChatGPT, and we're now fully in the age of AI agents. And yet the chat modality is still here with us, with far more staying power than many of us initially gave it credit for. Why is that? At CopilotKit, we've come to think of chat as essentially Slack with an agent. Chat is an open-ended communication medium between intelligent entities, which doesn't limit you to some predefined ideas with buttons and menus. It's also how people communicate. It's how we communicate with each other and sometimes even with ourselves. And so all signs are that chat is here to stay with us for the long run of the agentic revolution. But chat doesn't have to be text only. It can be augmented by generative UI and in-app interactions, and it could even be anchored in voice or video rather than text. The ideas we explore in this course are likely to form our foundation that will continue to hold as the chat medium evolves. You've likely built a basic chat UI before, even if only in a Streamlit app while debugging your agent. The chat app you will build in this module is different in two major ways. First, it is built atop a robust, production-grade foundation that you will be able to continue to expand on to build full-stack agents and generative UIs. Second, you'll be able to use the chat setup you'll create here with practically any agentic backend solution across any programming language, any LLM provider, and any agent harness. As the ecosystem evolves, you will also be able to bring the same setup to any front-end environment. We will continue to expand on the foundation we will build in this module throughout the remainder of this course. This course will assume that you already know how to build an AI agent. We will provide a pre-built agent, but deep learning has lots of great resources if you want to learn how to build your own. In this lesson, we will build a LangChain Deep agent that we will deploy behind an AGUI fast API endpoint built in Python. We will build a React frontend using Copilot Chat component, which ships with CopilotKit, and which provides a fully featured chat component that works out of the box. Lastly, we'll connect our frontend to the agent via the Copilot runtime, which in this setup, we will host on a Hono server, which is a lightweight TypeScript server. In production, you can host the Copilot runtime on essentially every standard server setup. The Copilot runtime setup is technically optional, but it is highly recommended for production deployments due to a combination of security, performance, and scalability requirements. Every piece of technology used in this setup is fully open source. After we get our LangChain Deep agent running, we'll add an additional Google ADK agent and connect it to our frontend, so you can learn firsthand how to swap and add agents into your own applications. This flexibility is made possible by the AGUI protocol. So what is AGUI? AGUI stands for the Agent User Interaction Protocol. It's an open, lightweight, event-based protocol for facilitating interactions between agentic backends and agentic frontends. Under the hood, AGUI-compatible agents emit AGUI output events as they run, and they accept AGUI input events emitted by frontends in response to relevant user interactions. The AGUI protocol was born from our partnership with LangChain and CrewAI. This means that you can use these agents side by side in any user-facing application. Let's jump into some code and see it in action. We'll begin by setting up our project dependencies. First, we'll install the Python dependencies from the requirements.txt file. Then, we will install the front-end dependencies. And finally, we will load the API keys using our helper function. Next, we're going to start by building the agentic backend, the agent itself. We're going to start the server, First, we'll just create a standard fast API server. Then we'll create a LangGraph AGUI agent. This is an AGUI compatible endpoint for your LangGraph agent. Now remember, LangGraph is the framework underneath all of LangChain's agentic solutions. So under the hood here, we're actually going to be using a LangChain deep agent, but it is implemented on top of LangGraph, and therefore we're using the LangGraph AGUI agent. Then we're going to bind our LangChain AGUI agent into the root path of our fast API server. Finally, we're going to start our server on port 8002. You will notice that each lesson uses a different port so that they don't override each other. All right, now we have our basic skeleton for our agentic backend setup. We're now going to populate it with an actual agent. First, we will define that agent. We're creating a standard LangChain deep agent. Everything about this setup is completely standard, except for one part that I want to call out, which is we are injecting CopilotKit middleware into the LangChain agent. Middleware is a standard concept in the LangChain universe, and the CopilotKit middleware allows us to connect our LangChain agent to everything AGUI. Finally, we're going to set the graph of our previous LangChain agent to the graph of the agent we just created. And that's it, we're running. Now that we've set up our agentic backend, we're going to get started with the agentic frontend with CopilotKit. We're going to start the frontend, and we're going to use our standard helper started frontend function. By the way, if you're curious, you can check out the helper file, but it really just has a lot of standard boilerplate for the standard operations we're going to take on here. Now our frontend is up and running in port 3002. You'll notice the read the logs statement in this output cell. If you ever run into an issue with your frontend, you can check out this devlogs.txt file for the full logging generated by the frontend. You can view the frontend app by clicking on the link you saw before, but for convenience, we're also going to display the iframe embedded right within the Jupyter Notebook using the display app helper function. You'll see here that the initial state of the frontend is an empty app that just has a text in the middle of it. There's no Copilot, there's no agents, just an empty starting point. We're going to continue by setting up the Copilot runtime. The Copilot runtime is a backend that sits in between your frontend and your agent for security, performance, and engineering scalability reasons. It is technically not absolutely required. You could connect your frontend directly to your agent, but for production environments, we highly recommend using the Copilot runtime. The first thing we're going to do is import the LangGraph HTTP connector from the AGUI package. We're then going to use this connector to point at the LangChain endpoint we set up earlier at port 8002. Now we're going to set up a new Copilot runtime instance. You'll notice that when we set up the Copilot runtime, we specify a dictionary mapping between agent IDs and actual agent endpoints. We're setting up the LangGraph agent under the default ID in this case. Your frontend can specify which agent it's talking to. If no agent is specified, the default agent is used. Then we're going to create an endpoint using our Copilot runtime and set its base path to /API/CopilotKit. And lastly, we're going to serve this application using a Hono server. Now we've got a Copilot runtime running and we've got an agent running. It's time to bring the front end up to speed. We'll begin by wrapping our application with the CopilotKit provider. When we set up the CopilotKit provider, we point it at the runtime URL we just set up in the step before. Remember, /API/CopilotKit. Any part of your application that talks to agents must be wrapped by a CopilotKit provider. You could do this on a page-by-page basis, but it is usually easiest to do this in a single place in your layout.tsx file. So you can wrap your entire application once and then talk to agents anywhere within it. Next, we're going to set up the Copilot Chat component. Copilot Chat is a built-in, fully featured chat component that ships with the CopilotKit packages. You can fully customize it using custom CSS or custom subcomponents, although we will not be covering that in this course. Or, should you choose to, you could use the use agent hook to build a fully featured chat interface from scratch. Now that we've set up the chat, let's give it a try. Hello, how can I help you today? All right, we've just built a chat that connects to a real LangChain agent. Now, remember, AGUI lets you connect to any agentic backends out there. So we're now going to demonstrate this by connecting the same application to a Google ADK agent. I'm going to set up an ADK agent. First, we're going to create a standard Gemini ADK agent by importing the LLM agent from the standard Google ADK packages. Next, we're going to set up an AGUI server for this raw agent. We're using the ADK agent class imported from the AGUI ADK package. Next, we're going to set up a plain old fast API server and add our AGUI endpoint for the Gemini agent to its root path. Finally, we're going to start the server in port 8009. All right, so now we have our old LangChain agent running in the background, and we have another agent that is being served with its own fast API server in port 8009. We're now going to update the Copilot runtime to register this new agent. Because we're using TypeScript inside of this Jupyter notebook, we cannot update the code from before. We must overwrite the file altogether. The majority of what you see here is identical to what you saw before. Let me highlight the two places where we've changed the code. First, we're going to set up a connector to the agent endpoint we just set up, running at port 8009. And then we're going to add it to the dictionary of agents served by the Copilot runtime, this time under the Gemini ID. There's nothing special about the Gemini ID. You could use any string you want. Now we're going to update the front end to use the new Gemini agent we've set up. Once again, because we're editing TypeScript files, we have to override them. You will see here, the only change we're making is that we've changed the agent ID to point at the Gemini identifier that we set up earlier for our Gemini agent. That's it. Now let's display the app one more time. And let's ask it, what model is it powered by? All right, it's a large language model trained by Google. For those who don't know, Google is the maker of the Gemini models. So you see here, we took an existing chat UI and pointed it at a different agent with almost no work at all. That's it. On to the next one. In the previous lesson, your agent could only respond with text. In this lesson, you'll go beyond text by building with controlled generative UI, which is the workhorse of the generative UI spectrum. In controlled generative UI, you, as the programmer, define fully custom components, which the agent can then use and populate with data. You, the programmer, control the look and feel, and the agent controls the intent. All right, let's get to it. Going beyond text gives your agent an immediate communication advantage. For instance, what was previously a long and indecipherable wall of text can instantly turn into a clear and concise table or a pie chart. Controlled generative UI is the most straightforward and most widely used variant of generative UI. Developers simply define a set of custom components that the agent is allowed to use in its replies, along with the arguments that those components expect to get from the agent. The technical setup would be incredibly familiar to any front-end developer because it mirrors the standard definition of any front-end component. Since each interaction requires its own component's definition, the controlled generative UI paradigm offers developers maximal flexibility once the component is displayed. Components can be interactive and trivially affect other parts of the application. And they can also be made pixel perfect to conform to any specs by your design team. The standard variant of controlled generative UI, which we will explore in this lesson, gives the agent the ability to decide which UI components to engage with and when. Controlled generative UI is considered the workhorse of the generative UI universe for a number of reasons. First, it offers full brand control because you can fully customize each component for pixel perfect designs. Second, when using controlled generative UI, your agent will never hallucinate a component you've not registered. At worst, it could call the wrong component at the wrong time or populate a component with wrong data, but these are far less likely to happen. Controlled generative UI is also the fastest and most reliable solution along the generative UI spectrum. All of these qualities make it the most suitable solution for your product's most used surfaces. It's a really great 80-20 solution. The primary trade-off of controlled generative UI is that every new capability in your application requires a new dedicated component definition, and so complexity of implementation scales linearly with the scope of the agent. Here's how controlled generative UI works under the hood. Each registered component is associated with a name, a description, and a list of arguments needed to provide by the agent in order to display the component. These parameters are converted to tool definitions. The AGUI middleware then registers these as front-end defined tools. When the agent runs, it sees those tools just like it sees any other tool. The agent can decide to call those tools when it wishes to display some content to the user. When an agent decides to call a front-end tool, the AGUI connection halts back-end execution and hands off execution to the front-end. The CopilotKit SDK then maps the front-end tool execution back to the React component it is associated with and displays that component to the user. Finally, if the tool returns any result upon interactivity, the result is passed back to the agent backend as a standard tool call result. In this lab, you'll learn to use CopilotKit's use component hook to register components with the agent, without the agent ever being directly exposed to a React abstraction or to code. The use component hook is straightforward. Simply give each component a name, a schema, and a React component or renderer, and that's it. You're done. You can define components in a centralized fashion when you initialize your React application, or you can register components in different regions and pages in your application. And these components will become active and available for the agent as the user traverses your application. If you're familiar with React hook dynamics, this hook behaves just like any other React hook, and all of the backend complexity is handled automatically by the framework. The use component hook explicitly demonstrates the clean separation of concerns of controlled generative UI. The agent decides when to display the component based on its name, description, and schema, and the programmer decides exactly what the component would look like and what interaction it would support by defining a custom React component or renderer. In this lab, we're going to register 3 components with an agent using the use component hook. We'll start with the name component, the simplest possible component registration, a hello world of sorts to get comfortable with a pattern. We will then register a pie chart component, where the agent doesn't just pick the component, it also figures out what data to fill it with. Finally, we will register a flight card component as an example of a pixel-perfect custom design. By the end of this lab, you will be able to register any React component so your agent can render it on demand. We're going to start by resetting the state of your notebook. Remember, this is just a helper tool in case you get into a stuck state, always worth trying to reset your state. Just like before, we're going to start by setting up the dependencies. This section is going to look very familiar. We're going to start by installing our Python backend dependencies. Now, we're going to load up our API keys using our helper function. These are set up for you automatically by the deep learning platform. Now that we've got everything set up, let's start the agent. First, we'll start our backend. It's now running in port 8003. We'll now use our helper function to start our frontend in port 3003. All right, now that it's running, we can click into that and play with it. Just like before, we're going to embed the iframe of this URL directly in our Jupyter Notebook for convenience, using the display app helper function. Now we've got the basic frontend that we set up in lesson 2 all set up for us. All right, the chat is working. We're now going to venture outside of pure text chat with Control Generative UI. Remember, in Control Generative UI, we as programmers register components that the agent can use when it chooses to. We're going to start by registering these components with the agent. In this, we've added 3 use component hook calls to our application code, registering 3 different components that are now available for the agent to call upon as part of its controlled generative UI toolbox. Let's go through each of them one by one. The use component hook takes 4 different arguments. The first argument is the name argument. This is the name of the component made available to the agent. The next argument is the description argument. This is a simple string, but it's very important because it tells the agent when and how to use this given component. In this case, we're telling the agent to show the user's name in a card. Just a short sentence here. But if you find that the agent does not display your component at times when you expect it to, you can continue to add this description to your heart's content. Some applications even have dozens of lines in this description, teasing out a very specific scenario in which the given component should be shown. The next argument is the parameters that this given component expects to get from the agent when it is called upon. This component, the show my name component, is the simplest component we can think of. So there is really just a single argument it expects, which is the name of the person. Its type is a string. We're using Zod to specify the schema of arguments this component is expecting. The schema consists of both argument names and argument types. In this case, the argument name is name, and the argument type is string. Zod is the TypeScript equivalent of Pydantic. The next argument is the actual renderer for this component. It's a function that takes the arguments we specified in the parameters and maps it to a simple React component. In this case, we're mapping the name argument that we specified previously to a very simple inline React component that displays this name. Now let's look at the next component, This next component is a pie chart component. And the description of this component tells the agent that it can use this component to display data in the form of a pie chart. The agent also sees the types of this component. It can infer from those types when and how that component should be used. In this case, we're importing the props of a pre-built pie chart component. These are standard React component props. And if you'd like, you can go and explore them to your heart's content. Finally, the render function in this case is taking a React component as opposed to specifying a function inline. A React component is itself a function which takes arguments of the props and returns a rendered React component. Lastly, we're registering a flight card component to show flights to the user. You'll also notice that we've added another hook call to our app code, use example suggestions. This is going to populate our chat with pre-built suggestions that we can click on so that we don't have to remember what to type into the prompt. And lastly, you will see we still have our Copilot chat component down here. Once again, you could customize this component with custom CSS or custom subcomponents, or build your own fully custom chat UI from scratch using the headless use agent hook. If you want to explore the source code of the pie chart and the flight card components, you can click into the front end folder, and under components, you'll find both of these components laid out. These are standard React components. There's nothing special there. Now we're ready to display the app once again. We'll once again embed the iframe right here in the Jupyter for convenience. Now we have 3 pre-built suggestions here. When we press one of the suggestions, it's going to populate our text with a pre-built prompt. Let's try the first one, show my name. You see that the chat added a new prompt. Please show my name in the chat. The agent does not yet know my name, so it's asking me, hey, what is your name? So I can display for you. Well, my name is Atai. And now it said my name. My name is appearing in blue background because it's no longer replying in text. It's using the show my name component we defined earlier, which shows my name in a text wrapped in a blue rectangle. Now let's move on to the next component, pie chart. You see here, when we click the suggestion, there's just a pre-canned text that goes in there. And the agent replied with a fully featured component that we rendered and controlled from end to end. Isn't that nice? Lastly, let's check out the last suggestion, the flight card. And we see here a flight component fully rendered. As you see here, these are just simple, straightforward React components. And so you can fully customize them to your heart's content and even make them fully interactive, including with other parts of your application. That's it. You've now mastered Control Generative UI, the workhorse of the Generative UI universe. In the previous lesson, you saw how controlled generative UI gives you full control and customizability, but it requires a dedicated component for every interaction. In this lesson, you'll take a different approach called declarative generative UI. We will use A2UI, which is an open spec for declarative generative UI, led by Google, in which CopilotKit has deeply collaborated on. Instead of building a component for every single use case, you'll define a catalog of Lego-like building blocks and let the agent assemble those on demand. This is an exciting part of the generative UI spectrum. So let's dive in. In the previous lesson, we defined a dedicated React component for each item that we wanted our agent to support. The benefit was great control over each and every item shown. The problem is that every new capability requires a new dedicated component built from scratch, which is fine at 20 components, but quickly becomes painful at 200 components. Declarative generative UI flips this equation. Rather than defining each component individually, we define an upfront catalog, which we then let the agent assemble together on its own. Let's dive into what this means specifically. First, as we mentioned, developers declare a catalog of components, which should be thought of as Lego-like building blocks. The catalog is defined in 2 parts. First, there are definitions for each atom in the catalog, which include the item's name, description, and its required props. And separately, there are renderers defined for each item, which take a JSON payload describing each component and return an actual rendered component for the relevant platform. In this lesson, we will use React, but the same pattern extends elsewhere. When a user asks some question, the agent may decide to answer that question by assembling together a declarative generative UI component. The agent first emits a schema, which is a structural assembly of items from the components catalog, which is not yet populated with data. Then, the agent emits the data bindings that populate that schema with specific values. Finally, the schema and the data bindings are passed on to the front end, where they are served as inputs to a renderer, which returns the fully assembled component for the native platform. Again, in this case, we will be using React. The end result is a component which can vary considerably, but within the confines of a bounded menu that you control. Declarative Generative UI has a number of distinct advantages. First, it offers flexibility, but with guardrails. Your agent can render custom components for a job, but will draw from a fixed menu of pre-created components, which can be made, for example, to conform to your design guidelines. Additionally, because Declarative Generative UI is rooted in a structured schema, typically JSON, it is suitable for any front-end environment, not just for web, but also for mobile, Slack, and other environments. At the same time, Declarative Generative UI is less predictable and customizable than fully controlled Generative UI. This unique profile of strengths and weaknesses makes Declarative Generative UI most suited for the long tail of product surfaces in consumer-facing applications, where flexibility is generally more important than pixel-perfect designs and predictability. It's also suitable for internal applications, where functionality and simplicity of implementation often take precedence over an optimized experience. For example, if you're an airline, you will likely want your flight card to be implemented with controlled generative UI for maximal predictability as well as control of your application's most used surface by far. But if you think about features like tracking a lost laptop or getting refunded for a trip, it's more important that the agent can talk and interact with those abstractions at all than that it offers a pixel-perfect experience. And so these surfaces are great matches for Declarative Generative UI. In this course, we will implement Declarative Generative UI using A2UI. A2UI is an open Declarative Generative UI spec that is led by Google and which CopilotKit has closely collaborated on. A2UI implements the Declarative Generative UI approach we outlined earlier with a component catalog, a schema, data bindings, and renderers using A2UI operations. AGUI middleware is fully integrated with A2UI, which means you can bring A2UI Declarative Generative UI to any agent in the stack. Declarative Generative UI comes in two flavors, dynamic and fixed schema. With a dynamic schema variant, the agent is responsible both for assembling the schema on the fly and for populating that schema with data bindings. With the fixed schema variant, you as the programmer are responsible for defining the schema in advance, and the agent is only responsible for populating that schema with data bindings. Now let's jump into some code and take a look at how this works. First, just like in the previous modules, we're going to copy the reset session cell and run it to make sure we're starting from a fresh starting point. Next, just like before, we're going to set up our dependencies, starting by installing the Python dependencies, followed by the front-end dependencies. Now that those are installed, we'll load up our API keys using our helper function. Remember, those are pre-set up for you by the deep learning platform. Now we're going to build the agent. We'll start the server that's going to serve the agent. Now, just like before, we're going to start with our scaffold server. That's it. Our Fast API scaffold server is running. We're now going to actually serve a real agent from it after we define it. This time around, we want the agent to query for and use data before it responds with any declarative generative UI components. To simulate this, we're going to define a get sales data tool that the agent can call in order to fetch sales data in that given time. In a real application, this would query some API or a database. In this example here, we're just hard coding some sales data for the agent to use. This is not our core focus. So if you're not sure what we're doing here, you can come back to this point later. Now that we've created the tool, we're going to create an agent. Just like before, this is a standard LangChain deep agent powered by GPT 4.1 model. We're giving this agent now the get sales data tool. And just like before, we're passing it the CopilotKit middleware. You can read up the system prompt of this agent. As you see here, the agent is simply instructed to use the Generate A2UI tool to visualize data for the user. Now we're going to set up our front end with A2UI rendering. Just like before, we're setting up our Copilot runtime. Most of the code here is very familiar. We're setting up a standard connector to our LangChain agent that we set up on port 8004. And we're initializing Copilot runtime with that agent as the default agent. You'll notice the only real addition that we did not have before, which is the A2UI configuration with a flag of inject A2UI tool set to true. Under the hood, the LangChain A2UI agent can talk A2UI by calling a specialized tool. This tool is propagated by the CopilotKit and AGUI stacks. By default, it will be included. If for any reason you do not want to include this tool automatically, you can always exclude it by passing false to this argument. We're now going to define our declarative generative UI component catalog. Remember, the component catalog consists of two parts, the component definitions and the component renderers. We'll begin by populating the component definitions. Now, don't get scared. We're going to paste a big chunk of code, but we're going to scroll right to the top and explain what it is that we pasted in a moment. All right. This is our demonstration catalog definitions. You see here, there is a dictionary of components with their definitions. The first component here is the title component. It has a name, title, a description, in this case, a heading, used for section titles and page headers, and props, typed schemas using Zod schemas, like before, for communicating the types of arguments this component is expecting. You see here, we have a very long list of components that we're defining. Title, text, icon, image, and so on and so on. This is one of the inherent costs of declarative generative UI. You have to set up all of your Lego-like building blocks up front for your agent to be able to assemble them together. We won't go through each one of the components here because conceptually they're all the same. We're now going to define the renderers of our components. Once again, we're going to paste a long file first and then scroll up and walk through it. The beginning of the file consists of imports that are going to be used by our renderers and some helper functions, once again used by our renderers. If we scroll a little bit down, we'll see the actual catalog renderers. First, you see that the catalog renderers is a generic type that specifies the catalog definition as its type parameter. This ensures that the renders perfectly match the types of the components that we defined earlier. Now you'll see that each one of the components we previously defined has a renderer. The renderers are simple React functions. For example, let's look at the title render. You see that it takes a props argument. Props contains the types we defined earlier, and then it simply returns a React component using these arguments. As you see here, there is a long list of component renderers, one renderer per each component we defined earlier. These custom renderers is how you can get your own custom stylings when using declarative generative UI. Simply make your component renderers aware of your design style guides. Now let's scroll down to the bottom of the renderers file. Quite a few renderers in there. All right. You now see the demonstration catalog definition. We use the create catalog function call, and we pass to it as arguments the demonstration catalog definitions and the demonstration catalog renderers, which we created just now. Finally, we're giving it the catalog ID of app dashboard catalog. All right, now we have our catalog definitions in place, and it's time to wire it up. We're now looking at application code that should look very familiar. Once again, we're wrapping our application with the CopilotKit provider so we can connect to agents anywhere within it. The only difference is that this time we're passing the CopilotKit provider another argument, the A2UI argument. In the A2UI argument, we're passing the demonstration catalog that we just created. This tells the agent it can use this component catalog when composing components together. Now we'll wire the Copilot chat component back into our application, along with some example suggestions, then once again, simply hardcode a set of prompts into the chat. Having defined the frontend, we'll now start it. We'll use our start frontend helper method to start the frontend on port 3004. Now that it's running, we'll once again embed its iframe inside of our Jupyter notebook for convenience. All right, our chat is now live. Let's test out some declarative generative UI rendering. First, we'll click Sales Dashboard. You see here, when we click the suggestion, we simply got a pre-canned prompt. All right, the agent dynamically combined a bunch of the components we defined in our catalog together to show us this great sales dashboard. We see here the total revenue with a title and then a text, new customers, conversion rate, and even a pie chart and a bar chart. This is an example of dynamic schema declarative generative UI. The agent first assembled a schema from scratch, putting together a bunch of the components from our component catalog, and then populated that schema with data bindings. We're now going to see an example of fixed schema declarative generative UI, where we, as programmers, hardcode a predetermined schema in advance, which the agent will simply populate with data. The first step in fixed schema declarative generative UI is, of course, defining the schema. Where is the schema going to come from? Well, you're not going to want to handwrite it. The schema file is a big, messy JSON schema that is designed to be written by machines. There's a great tool in the A2UI ecosystem called the A2UI Composer, which essentially includes a copilot that helps you assemble a schema to match some parameters. We're going to drop screenshots for this A2I Composer into the Jupyter Notebook, and you can find it on a2ui.org and then click on the Composer. This picture is what you'll see when you go to the A2I Composer. There's a simple chat input box that lets you specify the type of component you want to build. After some iterations, you'll end up with a schema. The Composer shows side by side the schema, sample data bindings that you can edit if you'd like, and a preview of what the rendered schema plus data bindings would look like. After some iterations, you'll end up with a schema to your liking. When you've done that, simply copy its JSON and prepare for the next step. We're now going to add a tool that returns a fixed schema declarative generative UI component. You will want to paste the schema definition you got from the Composer into a variable somewhere in your application. If you look here in the detail, you will see the rough shape of assembly of components together. But once again, this is not code that you want to be handwriting. Another detail you notice here is the catalog ID, referencing the component catalog we defined on the front end, and a surface ID. The surface ID identifies a specific A2I component. It's useful because it allows components to be updated, not just appended to. We're going to create a dummy search flights tool for the agent to find relevant flights for this user. In a real application, this will be hitting an API or a database, but for the purposes of example, we're simply going to hardcode some data here. Now, we're ready to define the tool that will return a fixed schema declarative generative UI component. As you will see, any component whatsoever can return such components. First, let's look at what this tool returns. This tool uses the a2ui.render helper function to return an array of a2ui operations. The first operation creates a new surface using our surface ID. The second operation updates components for that surface using our flight schema. And finally, the third operation populates the data for the components using the flights arguments passed to this tool. Remember, in fixed schema declarative generative UI, we as programmers predefine the schema, but it's still the responsibility of the agent to populate the data for that schema. It's critical that the shape of the data we pass to the component matches the shape of the data expected by the schema. In order to ensure this happens, we have our tool take an array of flight arguments whose shape exactly matches the shape defined in our schema. Now that we've defined our tools, it's time to create our agent. Once again, we're going to create a simple LangChain deep agent. If you look at our list of tools, you will see the tool we defined previously, get sales data with mock sales data, as well as two additional tools. The first one is the search flight tool, which provides mock data for flight information. Once again, in a real application, this would be collecting to an API or to a database, as well as the display flights tool. The agent can call the display flights tool in order to show the A2I component to the user. Once again, we specify the CopilotKit middleware, and we include a system prompt that tells the agent how and when to display components. If you're curious, you can read this in more detail. Here, we're adding chat suggestions to let users easily search for flights. Now that we've defined our fixed schema tool, let's take a look at our application. The front end is exactly identical to what we saw before. But now that we've given our agent the ability to search and display flights, let's see what happens when we ask it for some flights information. Good job! The schema you created in the Composer is now live on your screen, having been populated by the agent. We're now done with this section. Great job! You now have experience working with declarative generative UI. You first defined a component catalog, which is specified by a combination of component definitions and component renderers, and then exercise that component with both dynamic schema and fixed schema declarative generative UI. As a reminder, each declarative generative UI component is specified by a combination of a schema relative to component catalog and data bindings relative to that schema. In the previous lessons, you constrained what your agent could show through specific components in the case of controlled generative UI, or through a catalog of building blocks in the case of declarative generative UI. In this lesson, you'll take a different approach by removing these constraints on your agent's UI. First, you'll connect your agent to MCP apps, letting it hand off control to third-party applications, the same applications that are built for the ChatGPT and Claude app stores. We will follow up by exploring fully open-ended generative UI, where you allow your agent to create brand new interfaces on the fly. Fully open-ended GenUI really captures the full promise of how GenUI could continue to evolve. Let's get coding. The first type of open-ended generative UI we will explore is MCP apps. Instead of building a UI for every new capability, with MCP apps, you simply connect your full-stack agents to third-party applications that already exist and which come with their own UI and branding. As a developer, you only need to wire up the MCP apps, which are then made available to the agent. The agent then decides when to call on those apps and how to interact with them. MCP apps are the standard supported by the ChatGPT and Claude app stores, which means you can bring the same applications your users are using in these environments to your own custom agentic applications, including Figma, HubSpot, Excalidraw, and so on. MCP apps are implemented via a three-part architecture. The first part is the MCP server. With the MCP apps extension to the MCP protocol, the same server that serves your familiar MCP tools can now also serve UI resources. These UI resources can then be assembled into an iframe web representation. Second, you have your host front-end application. The UI resources are embedded inside of a double iframe for isolation and security purposes. The third part is, of course, the MCP app view itself. This MCP app view is isolated from the rest of the application, and it may communicate with the host frontend via JSON RPC. It's worth noting that even though MCP apps are served by MCP servers, they are otherwise completely independent from the MCP tools returned by those same servers. This may be a little confusing because MCP apps evolved out of a previous standard called MCP UI, which did allow any MCP tool to optionally return UI resources from any interaction. But MCP UI has now evolved into the MCP apps standard, which again has fully decoupled the UI resources aspect from the MCP tools. The tools in the UI are served by the same servers, but they do not otherwise interact. The main reason to use MCP apps is to bring third-party applications from those ChatGPT and Claude app stores into your own custom agentic applications. MCP apps are highly optimized for that specific use case, including with its benefits, which allow fully custom branding from the outside and interaction with third-party services at the expense of some trade-offs. MCP apps are essentially an app designed to live inside of another app, which introduces meaningful indirection overhead. So you typically would not want to implement your own app's functionality as MCP apps. In a moment, we're going to embed the Excalidraw MCP server into your application, which will expose the Excalidraw MCP app to your full-stack agent. As you can see, there's just a single MCP server URL you have to deal with. There's no separate URL specifically for the MCP app. Finally, at the far end of the generative UI spectrum, we find fully open-ended generative UI, where your agent writes brand new applications on the fly, typically to be embedded inside of the AI chat. This part of the generative UI spectrum, of course, provides the most flexibility. You're essentially giving your agent full creative freedom. But this comes at a trade-off. Generation is slower and more error-prone. It is far less consistent and deterministic, and the quality of your result is highly sensitive both to model choice and even to the prompts and skills that you feed to your agent. Fully open-ended generative UI is still in the exploratory phase of adoption, but as the AI stack continues to evolve, it will likely fill a larger and larger role in the production stack over time. All right, let's get to the code. Just like before, we'll start with the reset lesson cell to make sure our notebook is in a clean state. And just like before, we'll begin by setting up our project dependencies. We'll begin by installing the Python requirements, followed by our front-end requirements. And finally, we'll load our API keys that are pre-provided by the deep learning platform. We'll now start the backend and the frontend just like we did before. We'll start our backend in port 8005. And we'll start our frontend in port 3005. Now that our front end is running, let's display it inside of the Jupyter notebook using an iframe for convenience. All right, you now see the same chat experience we defined before. Now let's add an MCP app to our basic chat. Like we discussed before, MCP apps is an extension to the MCP protocol that allows MCP servers to specify not only tools and context, but also applications that may be embedded inside of the chat. The code you're seeing here should look very familiar from before. There is only one point of addition we're making here. When we define the Copilot runtime, we specify an MCP apps parameter. Inside of the MCP apps parameter, we pass an array of MCP servers, which may serve MCP apps. The Copilot runtime will automatically access these MCP servers and determine if there are any MCP apps served from them. In this example, we're specifying Excalidraw's MCP app. You may be familiar with Excalidraw as a great tool for visualizing diagrams. That's it. That's all we have to do. Let's give it a try now. We'll display once again the updated iframe for our front end. Now, our chat has an Excalidraw MCP app to call on as needed. Let's give it a prompt and see what happens. Show me a simple network diagram of 3 routers, 2 laptops, and a server using Excalidraw. And there you have it, an actual Excalidraw diagram embedded right inside of your chat. As you see here, there's a few limitations to what we got out of this. Let's try to prompt it once again and see what we get. We'll ask it to add labels, titles, and generally make it as coherent as possible. All right, we're doing a little bit better. Our diagram now has some text and labels and arrows, but you see it's still not perfect. And this is a great demonstration of the trade-offs you get with open-ended generative UI. Generation takes longer, is less deterministic, and is more error-prone. An important tip here is that open-ended generative UI is the part of the generative UI spectrum most sensitive to prompts and to skills. You can often significantly improve the performance you get from open generative UI components by optimizing your prompt and your agent skills. Okay, now that we saw how easy it is to add MCP apps to our application, let's add fully open-ended generative UI to application as well. Once again, because we're using TypeScript in our Jupyter Notebook, we can only override the file altogether. Almost everything in this file is exactly the same as it was before, with one modification. We're specifying a new argument in the Copilot runtime definition, open generative UI, and setting it to true. Under the hood, when we do this, an open-ended generative UI middleware is injected to the AGUI stack. Just like with A2UI, open-ended generative UI is implemented by passing an additional special tool to our backend agent. This is propagated via the AGUI middleware stack. All right, let's give it a try. Once again, we'll display the updated front end as an iframe inside of a Jupyter Notebook. Let's try a crazy prompt. Hey chat, make it rain tacos. We see here that as the app is building, we're seeing it displayed part by part. And we have here something that looks like raining tacos. It's a little bit odd though. This shows another one of the trade-offs of open-ended generative UI. You never quite know what you're going to get on the other side. Let's try to improve the prompt. We'll ask the agent to use taco emojis that are more likely to resemble real tacos and to make the rain look a little bit more like real rain. All right, that's not too bad. There's still room for improvement probably, but it's not too bad. So there you have it, open-ended generative UI. To recap, we showed how we can easily integrate MCP apps that may be served by any MCP server into our application. And we showed how we can let the agent create fully open-ended generative UI on the fly to meet any prompt we throw at it. There are trade-offs to this part of the generative UI spectrum. It is slower, it is less deterministic, and it is more likely to result in errors. But it also really captures our imagination and points the way to where the generative UI world may evolve to. Great job. You've now gotten experience across the entire generative UI spectrum, all the way from fully controlled generative UI to declarative generative UI, and now to fully open-ended generative UI. In the previous lessons, you built agents that present rich UIs, but only inside of the chat window. In this lesson, you'll go beyond the chat window to build an app where the agent and the front end share live state. We will build an agentic take on the classic to-do app, where the agent creates to-dos from the backend, users edit or complete those in the front end, and both sides stay in sync automatically. This state synchronization is the foundation for building your own Claude Code or Cursor-style application across different verticals, from legal to accounting to marketing to you name it. So let's get to it. We are now venturing beyond the isolated chat interaction to explore fully featured full-stack agents, which are designed to feel like true coworkers. It turns out that a small set of agent-user interaction primitives are used by virtually all successful full-stack agents. Before we explore a couple of those technical primitives, it's worth taking a step back and briefly asking what makes for a great full-stack agent from a product standpoint. Of course, a great intuitive user experience is the foundation. As we mentioned before, there is no reason to run away from the chat modality which is taking the world by storm. And remember that chat also does not mean text-only interaction. You want to build augmented chat, which leverages generative UI, voice interactions, and perhaps even video. A great chat experience also gives users visibility into what the agent is doing, to keep them engaged, but more importantly, to earn users' trust and to give users the opportunity to steer the agent to better address their needs. So this is a good place to experiment. Just as critically, chat as the anchor of agentic interaction does not mean that chat exists in isolation. The agent should feel like a native part of a larger application. It should be able to leverage any data, context, connectors, or actions associated with the application at large. A good rule of thumb is that if an end user can take some action or learn some fact using the application at large, they should also be able to take that same action or learn the same fact via the chat. The agent must also have deep access to the application's real-time context, meaning to what the user is currently looking at and to the actions currently available to the user. We can tease out these qualities with a few examples. In Cursor and in GitHub Copilot, the agent isn't a chat window you switch to, it's integrated into the workspace itself. It reads your code, understands your project, edits files, runs commands, all without you leaving the editor. The agent and the tool are a single entity. In Notion AI, the agent is automatically aware of what's on the page. You don't need to paste context or explain what you're working on. It already knows because it's embedded in the document, not sitting beside it. In Harvey, a legal AI assistant, the agent doesn't just answer questions, it takes actions alongside the user, drafting documents, analyzing contracts, operating inside the same workflow the lawyer is using. Again, it's a collaborator, not a chatbot. It turns out that agentic applications across very different domains end up being built atop the same small set of core primitives. One of those building blocks is the generative UI spectrum that we explored in the previous lessons. In this lesson, we'll look at two additional technical building blocks: front-end tool calling and shared state synchronization. We will explore them from two perspectives. First, from the standpoint of developer SDKs you should know about in day-to-day development, and second, conceptually, so you can understand how these primitives work under the hood. First, front-end tool calls. Front-end tool calls are directly analogous to the standard back-end tool calls you're likely already familiar with. The difference is that they allow an agent to execute an action directly in the front-end application, not just where it's running. In React, you register front-end tools using the use front-end tool hook, specifying the arguments expected by the tool and the handler to be executed when the tool is called. If your handler returns a result, that result is passed back to the agent as a standard tool call result. You can register front-end tool calls in a centralized fashion when your application initializes, or you can disperse their definitions across different parts of the app so that they load and unload automatically as users traverse the application. Under the hood, these tool calls are passed to the agentic backend in a standard format. When the agent then decides to execute a front-end tool, AGUI recognizes that, pauses the backend execution, hands off control to the front-end, executes that tool, and then transfers control back to the agentic backend once execution is complete. Once again, you don't have to worry about all this complexity when developing. You simply call the use front-end tool hook. Next, shared state synchronization. By default, the agent and the front-end are disconnected. The agent does not know what the user sees, and the front-end does not know what the agent knows. Shared state is the primitive that solves this. To use shared state synchronization, use your agent's standard state abstractions. In this lesson, we will use LangChain's agent state. On the front end, use the use agent hook, which exposes a reactively updated typed state object. Under the hood, here's how this works. As the agent runs, it can update its state. When it does so, it can then update the front-end state by emitting state delta events, meaning it communicates the changes that needs to be applied to the front-end state so that it remains in sync with the back-end state. These state delta events are themselves streamed because they're often generated by an LLM. The front end can also emit state delta events to support state modifications that are coming from the user. Finally, when needed, conflict resolution between the two states is handled via AGUI middleware. Once again, these are implementation details you do not need to be aware of in day-to-day development. Simply use the use agent hook. In this lesson, you will build a Canvas agentic to-do app that combines a chat interface with a traditional to-do board. You will expose a Open To-Do Canvas tool to the agent to allow the agent to interact with the application on the user's behalf. And you will use state synchronization to keep the front-end representation of to-dos synced bidirectionally with the agent's representation of to-dos. Let's look at the code. We're going to be building an agentic to-do app that will venture outside of the chat window to a fully featured full-stack agentic application. Just like before, we'll start with our reset lesson cell to make sure we're in a clean state. We'll set up our project dependencies, once again, starting with our Python dependencies, and followed by our front-end dependencies. Before we move on, we'll also load up our API keys that are provided by the deep learning platform. We're now ready to load back our familiar starting point by starting the front end and the agent server. We'll once again use a standard LangChain deep agent and serve it behind a fast API server. Now we're ready to start our front end. Once again, we have our basic chat set up and ready for modification and augmentation. We're going to amplify this basic chat with front-end tool calling as well as state synchronization between the front end and the agent. We'll begin by implementing shared state between the agent and the front end. First, we're going to define a schema for our agent state. Our agent state consists of an array of to-dos where each to-do has an ID, a title, and a flag indicating whether the to-do has been completed or not. We've defined our agent state. We're now going to define tools that will allow our agent to interact with its own state. The first tool we define is the Manage To-Dos tool. This tool lets the agent update its own state using the command function provided by LangChain. The second tool we provide is the Get To-Dos tool, which allows the agent to read its own state. Finally, we put both of these tools in an array so that we can easily populate them into our agent later. All right, now that we have the agent state and the tools defined, we're going to be updating our state to take advantage of those. This code replaces the previous agent we defined with a new LangChain deep agent. This LangChain deep agent is still very basic with a few key changes. First, it specifies a state schema using the agent state type we created earlier. Second, it specifies the to-do tools that are now made available to the agent. Lastly, just like before, we're specifying CopilotKit middleware to allow the CopilotKit and AGUI stacks to easily interact with the LangChain agent. Now that we've set up the agent, it's time to set up the front end to take advantage of this new functionality. Now we're going to introduce front-end tool calls to our agent, as well as bind the agent state we just defined to our front-end state bidirectionally. Once again, because we're editing TypeScript code inside of the Jupyter notebook, we must fully overwrite the file that was defined before. But let's walk through the changes we made. First, we're going to define a simple local variable that our application is going to take advantage of, to-dos open and set to-dos open, initially set to false. We're then going to define a front-end tool that's going to be made available to the agent so that the agent can interact with this local variable. We're using the Use Front-End Tool hook provided by CopilotKit, which connects to AGUI's front-end tool concept. And just like every other tool, this front-end tool can provide a name, a description, parameters, specified once again as a Zod schema. As a reminder, Zod is the TypeScript equivalent of Pydantic. And finally, our front-end tool can have a handler that will be executed when the agent decides to call this tool on the front end. Notice that the front tool handler can be asynchronous. Under the hood, whenever an agent decides to call a front-end tool, the AGUI middleware hands off execution from the agentic backend to the agentic front-end. Once a result is provided by the front-end, it is propagated back to the agentic backend, and the agentic loop continues. To recap what we did here, we created a local variable that allows the application to open a to-dos panel. Initially, this to-dos panel is set to false, and we give the agent the ability to interact with this variable via a dedicated front-end tool call. Now we're going to subscribe to our agent state using the Use Agent hook. Use Agent is an incredibly powerful primitive for the agentic age on the front end. It gives you everything you need on the front end in order to interact with agents, with all of the messy details automatically taken care for you. In this case, we're going to be using Use Agent's state variable in order to bidirectionally tie our front-end state to the agent state. Finally, we're returning the React component associated with this application now. The most important part I would like to point out here is the to-dos list component, which accepts a state getter and a state setter for its own to-dos. The state getter is simply reading agent.state.todos. The state setter is simply setting agent.state with new to-dos. This is quite profound. We see here that the Use Agent hook provides us with full-featured state synchronization between our front end and our back end. Just like local standard React state, the state is reactive, which we can take advantage of in our application. And every act of state update, streaming, and conflict resolution is automatically handled for us. As application developers, we can simply treat it as standard state as if it was just defined in our local application. Under the hood is automatically kept in sync with our agentic backend. All right, let's give it a try. Once again, we're going to use the display app helper to display our application inline. All right, you see here we have now a chat with a new to-dos button. Let's click it to see what happens. When we click it, we see a panel opening from the side with to-dos. Right now, there are no to-dos defined as of yet. If we wanted to, we could interact with this locally. Under the hood, remember, every time we do this, the agent.state is updated, and we can also close it and allow our agent to edit our to-dos for us. Remember, the agent can also set the to-dos open variable that decides whether the to-dos panel is open or closed. Let's ask our agent to set the to-dos to open and to create a number of interesting to-dos. All right, there you have it. We now had our agent open our to-dos panel and populate it with brand new data. This state synchronization works in both directions. We can edit our to-dos and ask our agent how many to-dos are still open and get a correct answer. Congratulations! You've now mastered front-end tool calling and state synchronization in addition to the full Generative UI spectrum you've mastered before. I'm extremely excited to see what you'll all be building. See you in the conclusion section for a quick recap. Congratulations! You've now built across the entire Generative UI spectrum. You started with controlled Generative UI, where you, as the programmer, had full control over every single component. You then moved to declarative Generative UI, where you defined building blocks that the agent could assemble on demand. You then connected your agent to third-party MCP apps, and you even explored fully open-ended Generative UI, where the agent creates interfaces from scratch. Finally, you built a shared state application, where the agent and the front end stay in sync beyond the chat window. The key takeaway is this: there is no one approach to rule them all. Each part of the Generative UI spectrum serves a different need, and now you have the tools to mix and match those in your own applications. And because everything you built uses the open source AGUI protocol, these patterns work across the entire agentic ecosystem, not just within CopilotKit. This course explored the first layer of the agentic front-end stack. But there's a lot more, from the persistence layer of all of this rich interactivity to the insight layer that allows you to understand how your users are interacting with your agents in production, all the way to the self-improvement layer that allows your agents to learn across interactions and improve on their own over time. We hope you'll join us to keep learning. You can start by exploring the CopilotKit docs or by joining the open source community. Thank you for taking this course, and happy building!